Good morning.
Good morning.
I'm so glad you're all here. I'm super excited to be here with my friend Jed and all of you.
Yeah, I'm really excited to be here. I love Rejects. This has become quickly my favorite conference. Yeah.
Absolute favorite. So what we both wish we knew about container security starts off with everything. But what we do know is a little different, right? Like sorry, I think I just went a little too far forward. So what I do know about container security is summed up in a couple of other things, right? Like one of the things that I'm going to start with is this really awesome idea of a cognitive bias that is the law of the instrument, right? Where it's like if you have a hammer, then everything looks like a nail. Frequently in our industry, that hammer is Linux, right? And when we think about containers as a thing that has evolved over time, that Linux hammer has come in very handy. And we've done a lot to improve that hammer, but it is very much leveraging Linux as that hammer. Some of the other things I know are that containers aren't real. Containers are just Linux processes. In that, like every Linux process, if you were to log into a Linux system today and look at all of those processes and look at the proc file system, you'd find that all processes in Linux today, as it is today, are associated with a bunch of namespaces. For the most part, if they're all under the same, if they're all like operating at the same layer of the Linux kernel, then they may agree on what all of those namespaces are. But if they're a container, then some of those namespaces will be different. But fundamentally, containers are just processes. You can't have a container that exists without a process inside of it. Another thing I know is that IP tables is complicated, and it's one of my absolute favorite quotes. You know, in any team, you need a tank, a healer, a damage dealer, and somebody who knows IP tables really, really well. A shared kernel is another thing about this, right? So when we talk about containers, containers actually have a lot of primitives, and we're going to talk about some of them in this talk that allow for better isolation between processes, but not necessarily better isolation between those processes and the Linux kernel. We rely on different technologies for that part of that part of container security, right? For the most part, when we talk about container security, all of the primitives that we run into more often, like these namespaces and all of that stuff, that's really just better isolation between applications, not between those applications and the Linux kernel.
Yeah, and I wanted to touch on that as well. The shared kernel is a big deal because the kernel is carrying a lot of weight in Linux, right? It's now kind of the de facto security boundary as well, and we'll kind of talk today and point out like why that has kind of become problematic.
It's a risky one because of things like file systems are complicated. So back in the day when we were running applications directly on a server, we had one file system. We might have we might jail particular file systems so that access via some like web interface, et cetera, or like a web server would hit a specific file system that was somewhat contained at the time. But fundamentally, like file systems are complicated. And containers that you're making use of today can actually not only make use of a file system that is specific to that process, but also make use of file systems that are in the underlying host. And it's actually very easy to create a container that has access to things that you may not actually think it has access to. And that's where I say file systems are complicated. Another one is that soft links are hard. It's a funny thing. A soft link basically points to a file path. A hard link actually points to an inode. So when you have something like a soft link that points to a file path, you introduce one of the ways to exploit containers. Actually, a pretty common way is to leverage a soft link and do what's called a talk-to attack, where basically you have the ability to change the link that is being represented and allow for access that you maybe didn't intend. But these are all of the things that we've mentioned so far are things that you can find on modder.org that have had to evolve in the Linux kernel because of real exploits that exist in container security today. So as a high level, those are all just things that exist that really represent some significant challenges as it relates to containers. So let's go back a second. Let's do a little time traveling. Let's talk about where Linux came from, because we're using that Linux hammer for everything. Let's just jump back for a minute and kind of talk about the history.
So even before Linux, we can talk about Unix, right? Unix is basically the grandfather of modern computer, grandparent. Linux, as we know it today, took inspiration from Unix, and as you can see, here we have Ken Thompson and Dennis Ritchie huddling over the first Kubernetes cluster way back in 1972, right? But a lot of the core Unix developer philosophies that are discussed in where this book or where this image came from, the art of Unix programming, are carried over to today's cloud native landscape, right? Fail fast, a bunch of the philosophical attributes, but not just the philosophy, right? Like the technology, the foundation of TCP/IP, file systems, the concept of portable applications. These were all developed in the 1970s. It might blow your mind, but tools like cat, chmod, chown, cp, et cetera, those were developed in the first edition of Unix back in 1971. And they remain in our toolbox every single day, right? So not much has changed, but the hyper-scaled distributed compute systems that we know and love today, like Kubernetes, are basically just leaky abstractions for what would become Linux.
Yeah. When Linux was introduced, it was actually introduced as a way of developing another operating system for desktop computers. It wasn't initially meant to be the thing that we literally operate the entire internet on top of today, right? And just think about that for a minute. Like, this was a multi-processor system. I mean, it was a multi-process system. It was trying to solve things like time sharing between processes and the existing hardware and that sort of stuff. But fundamentally, it was not like the original idea for all of this was not to create like this abstraction that would be the way that we think about hosting everything on the planet today, let alone getting to the point where containers are a thing. That's a lot of growth over the number of years, and there's a lot of lines of code involved in that. And one of the big takeaways for me when I think about container security is that all of that work represents areas where like perhaps things didn't actually evolve perfectly into things like containers, right? So we're highlighting so far, like with things like file systems and soft links and those sorts of things, these are things that have had to evolve over time because when we introduced the idea of file system namespaces, when we introduced the ability to actually mount things back and forth between them, we also introduced ways to exploit those things that didn't quite evolve perfectly over time. So it becomes an interesting thing. When we think about the history of that, so like back in the beginning of this, we didn't really have any of the primitives of containers. Really, I mean, the first thing that really existed that we play with today are things like IP tables. Was introduced in the late 90s. That was a rewrite of the original port from BSD for that was, I think it was like IP chains or something like that. It was an early version of this, but like IP tables were like the first like real thing that we kind of introduced, that we play with every day, that was introduced back in like 2000 in the 2.4 kernel series.
Which also highlights looking at something like a BSD, a Unix derivative, right? So like we're taking from the past and then bringing it to the future.
Yeah. The next thing that came along was the mount namespace. And this is where we're actually making use of all of those file systems. After that, a few years later, we kind of started getting into a bunch of the other namespaces, things like the PID namespace, the network namespace, all of that came later. And think about like the work that had to go into those base subsystems when these new ideas of container namespaces came along. So now you have the ability to create a new network namespace. How would IP tables work in that new construct, right? This represents a whole nother level of development against a relatively mature and well-known technology, right? Like we've got IP tables, it's working for us, there's no problems with it. Now we're going to introduce the ability to implement IP tables multiple times on the same host, just for funsies, right? Like what things can we do to actually relate back and forth between those two different implementations? Like what happens inside the network namespace versus what happens in the host namespace. Represents a lot of complexity.
Another example of that is the user namespace, which was added to the Linux kernel in 2013 and will officially land in the next 1.33 Kubernetes release. So
finally,
these things have been around a while.
Yeah.
They're not purpose-built. They're kind of added and then patched and then basically bolted on after the fact.
And iterated and iterated and iterated on. Yeah. So containers are introduced kind of as a thing by LXC in 2008. This was before Docker, but it was the idea of actually like they finally had enough of the pieces and parts to actually make the puzzle happen. We could create containers. Docker came along and like really changed the game because of the user interface, right? Like the ability to create those container images, the ability to ship those container images, the ability to start them up. That actually happened in 2013. So when we think about the overall timeline of all of this, it's just kind of wild. And one of the great points about when it comes to container security is like go back and look at what had to change to be able to support what we're using for containers today. And you're going to find those bodies in the closet. You know what I mean? Like you're going to find all those little sharp edges that you're not expecting, and likely you're going to find some things that might either fascinate you or frighten you, depending on which part of the puzzle you're looking at.
Yeah, and so far we've been looking at the history, but let's kind of put this back into context and think about this in the modern day, where this is applicable, right? So containers, basically a lot of patches and, iterations. They were never purpose-built for running untrusted code securely in a multi-tenant environment. Nope. But here we are, right? That's today's challenge.
That's what we asked them for. But the idea of like containers as a security boundary isn't necessarily new. Like as you mentioned, right? Like one of my favorite terms for describing this, and actually it appears in a variety of different verticals within our space, not just within container security, but also within like browser security and other things like WASM and all of that stuff, is this idea of sandboxes. And I think it's an almost perfect and infamous analogy, right? Because like if anybody's ever seen a sandbox, it's not great at containing things. Like the sand is everywhere. It's not like staying inside the sandbox. And so I think it's a really good way of like kind of conceptualizing it.
Yeah, there is prior art here in terms of sandboxing. It's not a uniquely containerized phenomenon. Things like the web browser, Chromium has had, different types of sandboxing like site isolation. I was looking up the documentation for it yesterday, and the definition is browsers must defend against untrustworthy web pages that try to attack other sites or access a user's machine. So they basically solve that problem by breaking up subcomponents into their own isolated OS process. But to me, this sure sounds like the same threat model as containers, right? Like now we have to protect against untrusted code and protect adjacent processes or containers from the unknown. We've been thinking about this in terms of, the browser for a long time, and those same concepts are, coming into the world of security, into the world of containers. There's a couple other examples that, folks in this room will probably be familiar with. Bubble Wrap is a, container sandbox. We actually, at Edera, just, released our own Rust-based implementation of Bubble Wrap called Styrolite. One thing that I did want to call out is there's an individual named Chris Palmer, and he had a really great talk on sandboxing and its limitations. And there he basically advocates for, sandboxing is great, but it can only get you so far. He worked on the Chromium team. He basically pushed sandboxing to its extreme, limit. And what they kind of realized is that, you need to really rethink fundamentally how you protect your, your applications. And in his talk, he kind of advocated toward moving, toward memory safety. And in this talk, we're kind of advocating towards, much stronger forms of isolation rather than like taking something that's inherently insecure and just putting it in a sandbox.
Yeah. One of the benefits of like the work that happened in the browser is that like they were able to be a lot more opinionated, right? They were in a position where they could say like, these are the constraints that an application, a website must live within to be hosted within this web browser, right? Where, like I think in the Linux container space, we have not been in that position necessarily, right? Like, we're I think it seems to me like we've been more focused on adoption and less on security. So getting back into the container security, the Linux container side of things, I do want to give a shout out to Julia Evans. If you have not seen the work that Julia does, definitely check it out. They wrote an entire magazine that actually gets into a lot of the detail around containers. This is a great example of it because it talks about all of those namespaces that I mentioned that we were talking about before, the mount namespace, the net namespace, UTS, IPC, all of these things represent, as I mentioned before, like the actual namespaces that are going to be associated with a running process.
Yeah, so even though these are namespaces providing this isolation, the key thing to call out here is that they're all using the same shared kernel, and that's the theme that we talked through throughout this talk.
Yep. Yeah, and so just because they're better at isolating between processes does not mean that they're necessarily good at isolating between the kernel. And so one of the early ways to solve this problem was actually to create a virtual machine that has its own kernel, but it comes at a pretty high cost, right? So an example, like this diagram kind of shows, like from the container perspective, all of those containers you're running up against the same Linux kernel. But if you wanted more isolation, then having some level of virtualization would probably be a better model.
Yeah, and when we talk about what this model looks like on the container side, it's really that we've kind of turned the Linux kernel into a security boundary, when it never was really meant to be a security boundary, but we all just kind of keep acting like it is. So if you think about it, like, at its core, from a process perspective in Linux, the process has to request, everything from the kernel. If it needs to create another process, if it needs to be able to communicate with another process, this is all mediated from the shared kernel, which basically means that a compromise to the kernel is a compromise to all containers, right? Since it's that shared system. And one thing that I wanted to quickly call out here is that, we're talking about asymmetric attack surfaces here. So if you think about the difference between containers and virtual machines, the container's main API or user interface is that kernel. The Linux kernel today is about 40 million lines of code, so there'll be some bugs there, right? It's not memory safe, it's got some issues. Whereas if you have a hypervisor and you're using a virtual machine model, you can use an example like Zen, which is a hypervisor that has about 150,000 lines of code. Are there bugs in there? Absolutely. But that's a much lesser attack surface than something that's constantly evolving and moving and as complex as the Linux kernel.
Okay. So we've said that the kernel isn't a particularly great security boundary. Containers aren't particularly good at this. So what can we do about it? So one of the things that was developed relatively early on was this thing called secure computing. And secure computing also ties into that whole namespace component, as we talked about in the browser and all of this stuff, this idea of being able to create a better boundary between a process and that shared resource that is the kernel. So SecComp actually introduces this idea of being able to say, if we think about the Linux kernel as an event-driven API, and I know what all of the API calls an application might need to make are, then I can create a list of the ones that I would allow for that application to make, and enforce it to live within those means. And if that list needs to change, that's where we start getting into some of the sharp edges around things like secure computing, because most of the time, the way that people leverage secure computing today is that you kind of need to know that list ahead of time, and you need to apply that list before the process starts, and then the process starts, transitions, and lives within the list that you've given it. And if it needs to iterate, if you need to change that list, you need to restart the process. There's no dynamic changing that. Now, a lot of that world has changed over time. It's another one of those areas where we're evolving. Like eBPF is one of those areas where we're starting to kind of change the way that this stuff works. And we'll talk a little bit more about that in a minute.
Yeah, and on the other kind of extreme side here of, isolation is like this concept of full virtualization, right? So if you've been familiar with things like VMware or, other virtualization solutions, that's the heavyweight approach. And a little bit of backstory here, just from my personal life. Back in the day, I was a SRE at Google, and that was pretty early on. This was before Kubernetes was a thing. One of the things that really blew my mind when I started in that role was I kind of realized that the workloads that were running weren't running under virtual machines. Google was deploying, obviously Gmail and search and all these things, but they weren't isolating them using something like VMware, and I was really surprised to hear that. But Google's goal at that point was to move fast, and it wasn't security, right? If you think about Google, they famously own their entire stack from silicon and their data centers all the way up to the software. They have a custom kernel, all that good stuff. So they were able to prioritize speed instead of security because they didn't have to worry about it at the time. Outside of Google, though, in the real world, containers look very different, right? They typically run in cloud environments where you're not running on your own hardware. You're typically running alongside other folks' workloads. That old adage, like the cloud is just someone else's computer, that very much applies for the vast majority of container users today. So the kind of middle happy ground here is something like what we call paravirtualization. So if you're not familiar with this concept, this is a concept that virtualization has been around for a long time, well before cloud providers or hardware enabled you to have hardware virtualization. But you can still get the same isolation out of paravirtualization. And as we kind of mentioned here is that the way that this works is the applications that run inside of a paravirtualized environment, they don't make a system call to a shared kernel, they make a hyper call to the hypervisor. And then the hypervisor is responsible for isolating and providing resources to those workloads.
And it's referred to as the Goldilocks zone because it represents, why are containers a thing? Does anybody, what is the thing that makes containers so popular out there in the world? It's speed, it's portability. A container image is small, it's easy to deploy, it's very, very fast, right? VMs suffer from all of those things. Longer startup times, harder to get the VM image to where it's going to go. You kind of need to have a full operating system to be able to support those applications you're hosting. Paravirtualization sits in the middle. You actually get all of the security boundaries for all of those things. You get all of the security benefits, but you don't necessarily need a full operating system, right? You can actually you can start these processes in a way that actually gives you a better security model without needing all of the overhead of an entire virtualization stack. Really interesting space when it comes to the security model of it.
So we're going to kind of dive into a couple technologies that Duffie and I have looked at, with all of this in mind, right? That containers aren't real, they're just, patches that have been made over time, and they weren't really purpose-built to, provide us with the type of security that we're interested in. So the things that we're excited about, not really surprising that we both work on them, is, in my case, I mentioned here that past is prologue, right? So technologies from the past are basically being adapted for the future so that we can, make the world a better place. Mm. And one of those things that, we're working on here at Edera is basically something called, Edera Protect, but really at the end of the day, we're a container native hypervisor. So we can run really, in any environment. We don't require that you have, hardware virtualization from your cloud provider, but we can still give you that same degree of VM-based isolation. So it's really taking the best of both worlds where you have the developer ergonomics of running containers. You can still go fast. Your developer teams can package things up and not worry about portability or where workload lands. But we're trying to really deliver on that key promise that Kubernetes made, which is I don't have to think about my infrastructure as a developer. I can write a untrusted application or a trusted application, or maybe I'm running one with vulnerabilities, or maybe it's multi-tenant, and I just don't have to think about isolation. I just essentially run that container, and my platform handles all the heavy lifting of isolation and providing security for it. And then just a quick shout out to another thing that we recently released. I just briefly mentioned it, which is we open sourced prior to Kubernetes, or sorry, prior to KubeCon, Styrolite, which is basically a Rust-based container runtime, or sandbox. And that's essentially what we use. It's programmatic. It has some interesting benefits. And that's what we use to actually sandbox the containers that run within our isolated virtual machine environment. So it's kind of like layers. We're not just putting things into an isolated box and then say, well, you can do whatever you want. We're looking at this from a security in depth. And a Swiss cheese model where, not only are we providing isolation, we're also giving you a sandbox inside of that isolation environment to run containers in a secure way.
Without breaking adoption, without breaking the ability for people to actually make use of this stuff, which I think is exciting. So stuff I'm excited about things like eBPF. eBPF gives us the ability to, I was talking about like the kernel as an event-driven API. eBPF gives us the ability to hook into any part of that event-driven API and pull out things like context. So one of the major use cases for eBPF today are things like observability. Just give me better context for what's happening at runtime, right? I want to understand at the socket level what connections are being made. I want to understand at the file system level whether it's the root file system or the container file system, I want to be able to understand when that file is being opened, where does it actually exist, right? I want to be able to look for behaviors that I consider to be behaviors that would match like a threat actor. And like, how can I fingerprint things in a way that can be determined to be normal when I don't have enough context to even understand at any real depth what normal means? eBPF gives me that ability to have the context necessary to do that. One of the other ones I'm really excited about is Tetragon. So eBPF fundamentally is actually pretty hard to implement. Like when it comes to like writing eBPF programs, it's actually pretty tough to do. And that's actually why I'm very excited about Tetragon. It's a framework that allows you to it provides a better abstraction for a lot of the stuff that I was just talking about. So Tetragon is a framework in that, like if you go to tetragon.io, you can see all the use cases that the open source Tetragon project actually supports. And there are a lot of really great examples, like say, for example, whether you want to deploy Tetragon on just a server that has a Linux kernel or whether you want to deploy it inside of Kubernetes. There's a lot of really great use cases around things like observability and being able to see exactly what's happening in the application stack. And also anything that you can observe in eBPF with Tetragon, you can also enforce. So if you saw a behavior that said, you know what, this guy is actually within this series, within this set of Kubernetes nodes where I'm running untrusted code, I never want a process to be able to access the file system of the underlying root file system, right? How would you write that rule today leveraging tools that you know about? So that you could enforce that. You could say like, on this set of nodes, nobody touches the root file system unless you're already there. Can't start a container that does it. How would you enforce that rule? In eBPF, in Tetragon, that's actually a pretty easy one to write. And there's a great example of that in the website.
Yeah, I was lucky enough to work on Tetragon with Duffie before it became 1.0, and I will say that we built it to be container native from the ground up.
Yep. So at the end of the day, we're better together, right? There's no single solution to things like container security. It's too wide a space. When I say container security, the first thing that should pop into your mind is like, which part? We're talking about the network? Is it the process part? Like, which part are we talking about, right? There's no perfect solution. One of the things that I want to be able to see this a little better so that I can actually read it. So one of the things that all of us learn at events like this one is that every complex topic is better learned together, right? When we're out there in the hallway, we're talking about stuff. It gives us the ability to broaden our own perspective and understand more of the problem than we could ever understand in isolation, only entirely on our own. So while we're here, get out there, meet people, come meet people at KubeCon, exercise the hall track. That's the most valuable part of an event like this, right? I say often that I can only learn things through my own perspective until you ask me questions. And that unlocks a whole nother level of learning that I would never have had access to without you. So thank you for being here.
Amazing talk. So a couple of questions if you really have some doubts. We have time.
Thank you for the talk. It's actually more about the product you mentioned and the virtualization. Is it hooking into something like KVM on the kernel and use the paravirtualized devices then?
Yeah, that's a great question. So we are not using KVM. Most virtualization systems are. The key caveat with KVM is, if we're talking about it from a security perspective, it still exists in the Linux kernel, so you still have that 45 million lines of code that you have to worry about. But the key thing is that KVM requires hardware virtualization support. So if you're running Kubernetes on a standard EC2 environment and you don't pay for bare metal, then you don't get the luxury of having isolation that's provided by the hardware. So we're utilizing Zen, which is a previous implementation of a hypervisor. It's what AWS was built on. And as a result, you can essentially run anywhere and have nested virtualization, even on a standard EC2 instance that doesn't have the hardware virtualization support.
But couldn't you also use nested virtualization with KVM?
As long as the hardware provides and supports it. There is nested virtualization support in KVM. I've heard that it's not production ready, but I don't have any personal experience with it.
I only know it exists, but I don't know how it's graded.
Yeah, I'm not sure.
Yeah.
Any more questions?
What do you think about WASM as a security boundary?
I think in my opinion, it's actually a very interesting space. We were talking about like the curve of adoption versus security and like some of the trade-offs there, right? Like if you're in a position where you can actually define the constraints of an application the way that WASM does, you're going to start from a better model. You're going to start from a better security model, but you're also going to start from a harder adoption model, right? Because it means that like to be able to like if you think about WASM just as a packaging technology to get to the place where you can package anything that you would build inside of a Linux container into WASM, it's still pretty hard to do today because you have to live within the constraints of a WASM environment or a WebAssembly environment, I should say. So I think it's actually a really good new technology. I wish that it were easier to adopt and it would see more adoption. I'm actually very excited about it, but I worry because of that adoption part of it.
Any more questions? No. Okay, I had one. So, what are your views on Firecracker versus containers? Okay, because Firecracker offers sandbox. They're lightweight. They're fast. So, what are your views in terms of security in using Firecracker versus normal containers? Because we are heavily relying on Firecrackers. 80% of our infrastructure is on Firecracker. So what are your views?
Yeah, I'm going to repeat what Duffy said about ease of adoption. We're bullish on containers. It is really the easiest way to get started. And Firecracker does require some additional work and has some requirements around hardware being available, hardware virtualization. So that adoption, if you think about it from a friction perspective, it's just enough friction where we, think that the adoption might slow a little bit as a result of that. But Firecracker is great. Our position is that if you run containers just generally, you should be able to get the same type of security benefits without having that additional hump of making things custom and getting things working with Firecracker.
Want to learn more about the things we're excited about? Come chat us up anytime during the conference, and we look forward to speaking more with you.
One more question. What would you consider the best network fabric and policy engine across functions, micro VMs, containers, VMs, and even physical?
Yeah,
and this is not an opinion. I mean, your opinion's fine, but I'm just kind of interested to know what would be the right approach here.
Yeah, today I don't think there is one. I don't think there is one product that tries to solve that problem across the whole set. The closest is probably something like Tetragon, because Tetragon is basically something that just operates at the Linux kernel layer. So there are elements of network policy that you can enforce leveraging Tetragon that would apply regardless of what you were doing underneath that Linux kernel. But there's no, as a sense today, I don't know of a single product that's trying to solve that problem holistically across all the things.
Great, thank you. A round of applause.
Thank you.